first of all, I will introduce our lab and what we do here and how are we planning to commercialize our technology. Then I will come to the sensors that brought us to the UWM Tech Challenge, what we do with our sensors and what we did in the Tech Challenge and what is our experience. So first thing, our UWM Biorobotics Labs is focused on using robotic technology to help the individuals with disabilities, especially in their upper arm and upper extremities. So we work with research on robotic exoskeletons, robotic manipulators, mobile robotic assistants, and collaborative robots. So for that, we are focusing to provide to the disabled individuals these rehabilitation exercises, assistance in daily life, tele-rehabilitation, and therapy. So this is some of our successful projects from our lab. So first one is we are classifying people's brain EMG data and classifying them to different activities of daily life, so that we can use any sensor to detect the EMG from brain and control a robot to perform that activity for them. Then there is the tele-rehabilitation therapy using our robot. This is a finished project. So we developed a method to provide therapy process at home using a Now robot, its sensors, and a smart AI that can be programmed by the therapist to give instructions to the individuals and observe their therapy process if it's going properly. And we are also working with multiple exoskeleton robots to provide rehabilitation and motion assist to upper arms and wrist and not fingers at this moment. Okay. So these were our successful projects, and these are our most ambitious upcoming projects that we want to commercialize. So at top left there is a exoskeleton robot that can be mounted on a wheelchair. So if someone is paralyzed or have full body disability, this robot can help them perform some tasks by moving their arm and also provide some rehabilitation exercise if necessary. Bottom left is a robotic arm mounted on a wheelchair to help you do various tasks of daily life. And the middle one is targeted to an hospital setting to provide continuous rehabilitation exercises without the direct involvement of a therapist. So these are the projects we want to commercialize as a startup. And we have some progress in the third one. We have a working prototype that we are using to talk with various hospital providers. So now for commercializations, we have participated in NSF iCorps in 2018. We have participated in SBI Ready in 2019, and we are getting help from UWM Research Foundation and Center for Technology Commercializations to do our next steps. So basically, we are like a pre-startup right now, and we want to commercialize our research. And as soon as we have some of our products, commercial products ready, we will move into a business setup. So now, what brings us to this tech challenge and what brings us here? So it's about sensors. Sensors are really essential in modern automation and energy efficiency, smart devices. Everything is possible because of the sensors. So if you want to make a industry completely automatic, you need lots of sensors to monitor every step of the process. If you want to make a smart home to save energy, you will need sensors to monitor every aspects of this home and make decisions based on that. So we also use a lot of sensors in our work. So our sensors are used from very basic tasks of the robotics like control, feedback, and user input to specified tasks like when we are making an exoskeleton, we need to make it so that its motions are comfortable for the user. So we need force feedback from users, and we are also trying to make collaborative robots because our robots will be working in very close proximity to humans. So we need a lot of different type of sensors to make a collaborative robot work. So we are using encoders for position feedback, force and torque sensors, internal proximity sensors, contact pressure sensors. We also need sensors for human presence detection and object detections. So this is what we have to work with right now. So we have access to industrial sensors. These are very reliable and go-to product for initial development. But these are also focused for industrial application. These are bulky. They have robust circuitry inside and have a full unit that we need to incorporate in our designs. That is really difficult for what we're trying to do because our robots are really small. These are not like large industrial robots. Our robots are like more commercial, consumer grade. So for that we move into the IoT and consumer electronic sensors. These are based on discrete sensor elements used in consumer electronics, and recently progress in IoT and industrial adoption of IoT have made these sensors more robust and useful for us, but it's still not fulfilling everything we need. So here's the next step of sensors that we are working with. So we need to have sensors that have flexible form factor, flexible dimensions. Sensors need to be deformable because these will be mounted on human body. Exoskeleton, these will come between exoskeleton and human body, so they need to be deformed by when users are using them. And also, to make our robots small and portable, we need to eliminate discrete sensor units, and we need to combine these sensors elements and our robotic structural elements in single components. And we also need to manufacture this in same process as we manufacture our robots parts. So these are the issues we are not getting with existing sensor technologies. So that's why we recently started a few projects to develop our own sensors. So first thing we plan to do is design a capacitive sensor matrix that can be embedded in layers of carbon fiber that is used to make our next generation of exoskeletons and robots. And we are also working with piezoresistive materials like some of the 3M piezoresistive materials to make a deformable force sensor that can be used in an exoskeleton to measure the human skin pressure. So if we mount an exoskeleton here, the contact between exoskeleton and human body, we need to we can measure the contact pressure with the sensors. We are also working with embedded Hall sensors. So we need to make a way. We need a way to correct our error when we are making a multi-robot collaborative device, or we are doing it. We are taking an object and manipulating an object. We need non-contact position sensors that can be embedded in our robot's body. Last thing, when we are doing this, we came across the MO Tech Challenge, and we decided to also participate there because the requirements for that Tech Challenge also seems to be overlapping with what we are trying to move into in sensor research. So the last project we have is flexible PCB-based modular inductive proximeter sensor that we proposed for the tech challenge. So this tech challenge was, I would say, really well defined. The problem was well defined by Eaton Corporation. So we have to focus our research to achieve the requirements given by Eaton. So they gave us dimension requirements, frequency requirements, and some functional requirements. They also have these requirements as to make the sensor more viable as a product. So we took these requirements and we worked out a solution for that. So this is the team that worked. So me and Asif, both of us are PhD students in UWM, and Ivan is undergraduate transfer student from Colombia. So he was here when we worked on this project, but he went back to Colombia to finish his degree. And we were supervised by Dr. Rahman, our director of the Biorobotics Lab. So flexible PCBs are really the recent development in consumer electronics. These are now being used inside tiny mobile devices and many other places where you need a flexible electronic solution, and it can also incorporate connectors and interconnect cables within one single PCB. So we choose that to make to achieve the requirements set by Eaton, as well as the flexibility and deformability requirements we need for our research. So this was the proposal we submitted for Tech Challenge, but now we have some further work that we can proceed with. These are the options that came up when we were brainstorming during our design process. So we left it out later because this will take a lot more time and research to explore these possibilities. So we can use parametric modeling and optimize our design more to get better performance out of our design. We used a magnetic core in our design, so we can explore the effect of changing the shape of that core and maybe find a way to focus the magnetic energy to a specific direction to get more range out of it. We can use different materials for magnetic cores. During our FES simulation, we observed that our sensor is operating really close to the self-resonant frequency due to the capacitance. So we can also explore that and find out a useful way to use that self-capacitance to increase the sensor ranges, and we can use different coil configuration. So as an award for the Tech Challenge, we understood that the next stage would be working with Eaton. So this is what we are proposing when to do have from Eaton as a help to further progress this research and this project to get a viable market product. So we need help from Eaton regarding design for reliability, because they have been designing sensors and they have been doing R&D for a long time compared to us. So we can learn a lot from them about how to design for reliability. They also know how, the application space really well, so they can help us prepare our sensor for real world conditions, and they can also help us through the reliability and stability test, what needs to be performed and how can we conclude what test gives us good results. And we will also need help from them about certification. We already talked with Dennis about this, and he's expressed interest. So this will be really good for us. And also, if we learn this stuff from them for this project, we can use this knowledge into our own own future products from robotics side. So that would be really helpful for us in this regard. So thank you everyone for giving us the opportunity to participate in this tech challenge, and thanks for inviting us here to talk.